Swayam Prabha. Digital India. Educated India.
Okay, in continuation of fundamental concept of graph theory, let us go to discuss the regular. Graph is said to be regular if maximal that is see delta g is said to be maximal degree and small delta g is a minimum degree, and if they are equal then it is said to be regular. If graph is said to be k regular if the common degree is k, and you check it out the neighborhood of V and return as ng of V or n of V and set of vertices adjacent to V. So, this is the pictures for 3 regular graph. Now, order and size. Order of a graph is written by number of vertices in G. N vertex graph is a graph of order n. The size of graph G written as E of G is the number of degrees in G. So, the notation is box n indicates the set 1 to n, and a proportion graph G, G is a graph and degree of vertex V in V, always add all the degrees vertex definitely twice of the edge set. Proof is summing the degrees counts each degree twice because each edge has 2 ends and contributes the degree at each end points. Next theorem, if k is positive, a k regular bipartite graph has the same number of vertices in each partite set. So, k is a regular bipartite. So, already explained k is a regular bipartite and it has the same number of vertices in each partite set. So, each partite bit so 2 partite set, therefore, it is bipartite and each partite set have the same number. Let G be a x comma y graph, xy by graph. Counting the edge according to their endpoints x yields E of G is equal to k of cardinality of x. If k is positive, then k regular bipartite graph has the same number of vertices, and if E of G equal to k into cardinality of x, then k into cardinality of x equal to cardinality of k into cardinality of y implies x equal to y and c 1 to many, many to 1. So, same thing will come, therefore, k bipartite graph has the same number of vertices in each partite set. So, this may go for the technique for counting set. You take a Peterson graph of as a 6 cycles, let G be a Peterson graph and being 3 regular, G has a 10 copies of K13. This is K13 claw. We establish a 1-to-1 correspondence between the 6 cycles of the class. Since G has a girth 5, every cycle F is induced subgraph. Therefore, the degree of vertex V equal to 3 and V in P of G, but girth 5 has no such an edge. So, another one is counting set is non-adjacent vertices have exactly one common neighbor and opposite vertices of F have a common neighbor outside F. Since G is a 3 regular, so the resulting 3 vertices outside F are distinct and deleting vertex F leaves a subgraph with 3 vertices of degree 1 and 1 vertex of degree 3, therefore, it is a claw. So, the common neighbor opposite vertices, if the neighbors are not distinct, therefore, degree of V is greater than 3. So, the technique for counting set is each claw H in G arises exactly once in this way. Let S be the set of vertices and degree 1 in H S is an independent set. So, the central vertex of H is already a common neighbor. So, 6 other edges from S reach distinct vertices. So, remove vertex set of G is a 2 regular. Since G has a girth 5, so G minus V of H must be 6 cycles. So, the 6 cycles yields the vertices are deleted. So, this is a girth of each neighbors, and these are all the 2 regular, and 6 cycles it has, see 6 cycles it has, and when the vertices are deleted, then the resultant is once again a graph. Now, the minimum number of edges in a connected graph with n vertices is n minus 1. So, every graph with n vertices and k edges has at least n minus 1 k components. Hence, every n vertex graph with fewer than n minus 1 edges has at least 2 components and is disconnected. Therefore, the contrapositive of this, that every connected n vertex graph has at least n minus 1 edges. This lower bound is achieved by the path Pn. Now, we have a theorem. A simple graph with n vertex is minimal of delta G is greater or equal to n minus 1 by 2, then G is connected. So, choose U comma V in vertex set and show that U and V have a common neighbor if they are not adjacent. If G is simple, then we have a cardinality of n of U is greater or equal to delta G, which is greater or equal to n minus 1 by 2, and similarly for V, and recall delta G is a minimum degree. Therefore, cardinality of n of U equal to d of U, hence cardinality of n of U greater or equal to delta G. So, if G is a simple with the n vertex graph with delta G greater or equal to n minus 1, the other way G is connected methodology is U and V are not connected, then n of U union n of V cardinality is less than or equal to n minus 2, and U and V are not in the union, and according to the note, if you intersection of 2 equal to n of U plus n of V minus n of U intersection n of V. So, this value is n minus 1 by 2, this value is n minus 1 by 2, and this is n minus 2, and so the value is greater than equal to 1, equal to 1 will come. Next, every loopless graph G has a bipartite subgraph with at least E of G by 2 edges. Now, we have a partition E of G into 2 sets x and y. Using the edges having one endpoint in each set yields a bipartite subgraph with bipartite x and y. Therefore, H contains fewer than of the edges of G incident to a vertex V. Then V has more edges to vertices in its own class than the other class, as illustrated like this. So, many to many like that, and these are all the ways we can have the end point in each set yields a bipartite, and as a subgraph, that is also illustrated. Next, every loopless graph G has a bipartite subgraph having at least E of G by 2 edges. So, moving V to the other class gains more edges of G than it loses, and using iterative improvement approach, when it terminates, then D of V is greater than degree of V over H and degree of over V by 2 for every vertex V in G. Summing these and applying the degree sum formula yields E of H is greater than or equal to E of G by 2. Example, so the algorithm need not produce a bipartite subgraph with the most edges, merely one with at least of the edges. Consider the graph in the next page of 5 regular with 8 vertices and n as 20 edges. So, the bipartition of x equal to a b c d and y equal to e f g h yields a 3 regular bipartite subgraph with 12 edges. So, the algorithm terminates here. Switching one vertex would pick up 2 edges but loss 3. So, this is one with the continue of bipartite graph. So, H, G, F, E is one set and A, B, C, D is another set, and connect H with other possibilities. So, H is what connected with all the vertices, right, and then the possibilities of the bipartite here, and we have a what the 12 edges with regular bipartite, and the algorithm terminates here. Switching one vertex would pick up only 2 edges but loss there. Next example, nevertheless, the bipartition x equal to a, b, g, h and y equal to c, d, e, f yields 4 regular bipartite subgraph with 16 edges. So, this algorithm seeking the maximal by local changes may get stuck in the local maximum. So, this is the local maximum, this is the global maximum of possibilities of connecting the all the vertices. So, next theorem, the maximum number of edges in an n vertices triangle free simple graph in the ceiling of n square by 4. So, let G be a n vertex and it is a triangle free simple graph. Let x be the vertex of degree of dx equal to k, and G has a no triangle, there are no edges among the neighbors of x. So, like that, no neighbors between the neighbors of x. Next, the other way, the summing the degrees of x to its non-neighbors counts at least one endpoint of every edge, where summation v does not belong to n of x into d of e greater than or equal to e of g. So, the sum over n minus k vertices, each having degree at most k, is e of g is equal less than or equal to n minus k into k. Now, we have a theorem. The maximum number of edges in n vertex triangle free simple graph is ceiling of n square by 4, and we have a proof. So, d of e counts at least one endpoint of the each edge, and then we have what connection of edges, and connect from x to other vertex, and there is a ending vertex, no neighborhood, and no edges exist between these. Similarly for rest of them, and some of them having, so at least one endpoint for the every edge will come. So, here at most k vertex can be connected with the other end. So, in this way we have another way, n minus k into k counts the edges of in k suffix n minus k comma k. So, we have now proved that E of g is bounded by the size of the biclick with the n vertices. Therefore, E of g less than or equal to n minus k into k, which is equal to the edges in k suffix n minus k k. So, this is the what corresponding graphs. Another way is moving a vertex of k suffix n minus k comma k from the set of size k to the set of n minus k gains k minus 1 edges and losses n minus k edges, and net again. So, we have 2k minus 1 minus n, which is a positive for 2k greater than n plus 1 and negative for 2k is less than n plus 1. So, thus, the edge set E suffix k suffix n minus k comma k is maximized when k is a floor of n by 2 or ceiling of n by 2. Next is theorem, the maximum number of edges in n vertex triangle free simple graph is the floor of n square by 4. Now, the product is n square by 4 for even n and n square by 4 for odd n. So, obviously, edge set is less than or equal to the floor of n square by 4. Therefore, this is the best possible, implies the edge set of it seems that the triangle free graph with the floor of n square by 4 edges is k suffix n by 2 and n by 2 both ceiling and floor. Next, degree. So, degree of a sequence is of a graph is a list of vertex degrees usually written in the non-increasing order, that is d1 greater equal to d2 and so on greater equal to dn. Example, this is a graph and a degree of sequence is, find out d of w. What is the degree is here is 4. Similarly, you go to d of x, d of w, d of w is 1, 2, 3, 4, d of y you take it 1, 2, 3 and d of z you take it 1, 2, d of v you take it 1. So, the degree sequence is like this. If you write like that, then we have a proportion, a non-negative integer d1, d2 and so on are the vertex degrees of some graph if and only if summation of di is even. So, necessary is when some graph G has these numbers at its vertex degrees. So, the degree sum formula implies summation di equal to 2 times of E of G, which is even, and sufficient is suppose that summation di is even. So, we construct a graph with a vertex set v1, v2 and so on vn. Therefore, degree of vi equal to di for all I and summation of di is even. So, the number of odd value is even from the arbitrary pairing of the vertices vi such that di is odd. For each resulting pair, form an edge having these two vertices as its endpoints. So, the remaining degree needed at each vertex is even and non-negative. So, it satisfies for each I by placing di by 2 of floor loops at vi. Next, graphic sequence. A graphic sequence is a list of non-negative numbers, that is degree sequence of some simple graph. So, a simple graph realized D means a simple graph with the degree sequence D. Next, a recursive condition. Say you have a list 2, 2, 1, 1 and 1, 0, 1 or a graphic, and the graphic K2 plus K1 realize 1, 0, 1. That is adding a new vertex adjacent to vertex degree 1 and 0 yields a graph with the degree 2, 2, 1, 1 as shown in below, right. 2, see this vertex having 2, this vertex having 2, this vertex having 2, but this vertex having 1, this vertex having 1 and the neighbors. So, here 1, 1 and 1 connected with this one is no 0, 1 like that. So, conversely, if a graph realizing 2, 2, 1 has a vertex w with neighbors of degree 2, 1 and deleting w yields the graph degree of 1, 0, 1. Similarly, test 3, 3, 3, 3, 2, 2, 1, we seek realization with the vertex w degree 3 having the neighbors of degree 3. So, delete 3 and the new degree will be reduced to 2, 2, 2, here 3 as usual and then 1. So, this is called it as a recursive. So, this exists if and only if 2, 2, 3, 2, 2 is a graphic. So, this is a recursive condition. You take 3, 3, 3, 3, 2, 2, 1. If you delete, it becomes what 3, 2, 2, 2, 2, 1 will come, because here reduce one delete mean one vertex keep as it is, rest of them will be 2, 2 will come and it goes like that. So, what happen if you so this is the picture. We reorder this and test 3, 2, 2, 2, 1 and continue deleting and reordering until we can tell whether the remaining list is realizable. If it is, then we insert vertices and the desired neighbors to walk back to the realization of the original list. So, the realization is not unique. So, this works the recursive. So, here the vertex having this is what degree of this one is 3, and like that you have to write the pattern, and corresponding if you reduce first one is 3, then it become 2 2 and the rest of them 1 1 will come, and finally if you delete it and we have 1 1 0 0. So, these are all the ideas of the recursive will come, right. So, if you delete this one, that becomes one of them is 3, another is 2 2 2 2 2 and 1 will come reduce. So, like that the pattern one by one reduce, finally we reached the 1 0 1 1 1. Now, we have a theorem. If n is greater than 1 and integer list d of size n is for n greater than equal to 1 greater than 1 and integer list d of size n is graphic, if and only if d is graphic, where d is obtained from d by deleting the largest element delta and subtracting 1 from its delta next largest element. So, the only one element graphic sequence is d1 equal to 0. So, for n equal to 1, this is proved trivial. N is greater than 1 and we have to check it out the degree of all the vertices, check d1, d2, d3 and so on dn, and compare with d1 and d2. d1 degree is greater than equal to d2 and so on dn. So, that the degree of the sequence, for example, you take d here is 3 and we have what 3 3 3 3 3 2 2 1, okay. So, this having the 1, this degree is 1 and this degree is 2 and this degree is 3 and this is 2 and this is 2 and this is 2 and this is 2. So, it goes like this. So, if you omit it d and then we have a 2 2 and corresponding 3 3 1 will come. So, g with d is 2 2 2 3 2 2 1 will come. So, based on that we have a statement n is greater than 1 and integer list d of size n is a graphic, if and only if d is a graphic, where d obtained from d by deleting its largest element capital delta and subtracting 1 from its delta next largest element. So, the only one element graphic sequence is d1 equal to 0. So, we add the new vertex adjacent to the vertices in G with the degree d2 minus 1 and so on d delta plus 1 minus 1. So, these di are the delta largest elements of d after delta itself. Note d2 minus 1 and so on d delta plus 1 minus 1 need not be the delta largest numbers in d. So, this is the new next vertex and this may not be the largest numbers. So, like that we can understand the sequence of the graphic ideas. So, for the next proof of the same statement, given a simple graph G realizing D, we produce a simple graph G dash realizing D dash. So, let W be the vertex degree delta in G and let S be the set of delta vertices in G. So, the desired degree is D2 and so on D delta plus 1. Therefore, D colon D1 D2 and so on D delta Dn, where this is delta and this is vertices. Now, we have a neighborhood of this one is S and delete to W to obtain G. So, that D such that D1 to D delta plus 1 and so on Dn. So, you call this as a delta and then neighborhood of W is S, Therefore, they are connected to W, and delete W, then we have next D2 minus 1 to D delta minus 1 and so on Dn. Otherwise, some vertex S is missing from n of W. In this case, we modified G to increase modulus of n of W intersection S without changing any vertex degree, and can increase at most delta times. So, repeating this convert G into another graph that realizes D and has S as the neighborhood of W. From G we then delete W to obtain the desired graph G dash realizing D dash. So, D colon D1 to Dn, if D1 is delta, so delta vertices of n of W not equal to S. So, some vertices are not connected to W, we make them become connected to W without changing their degree. So, like that combined together of some modification neighborhood of W is not in S, choose X in S and Z is not in S. So, W, Z are connected and Wx are not connected, and add Wx and delete Wz. So, we must preserve the vertex degree, and degree of X is greater than D of Z, and already W is a neighbor of Z but not X. So, there must be a vertex Y adjacent to X but not to Z. So, delete Wz xy and add Wx yz to increase n of W intersection S. Therefore, W to Z x to Y, this Y must exist and it becomes connected W. So, this way we can do what another way of writing the proof of the theorem. Next, switch, 2 switch. 2 switch is the replacement of pair of edges of xy and zw. So, xy and zw in simple graph means no loop and no parallel edges, and the edges yz and wx given yz and wx did not appear in the graph originally. So, that is the meaning of 2 switch. So, G and H are 2 simple graphs with a vertex at P, then the degree of V over G equal to degree of V over H for every V in V, if and only if there is a sequence of 2 switches that transform G into H. So, every 2 switch preserves vertex degree, so the condition is sufficient. Conversely, when the degree of V over G equal to degree of V over H for all V in V, we obtain appropriate sequence of 2 switches by induction on the number of vertices n. If n is less than 3, then for each d1 to dn, there is at most one simple graph of d of vi equal to di. So, for n equal to 3, we have the basis step. If n is greater than or equal to 4, W be the vertex of maximum degree delta. So, S equal to V1 to V delta be a fixed set of vertices with delta highest degree other than W. So, as per the proof of the theorem 31, some sequence of 2 switches transform G to a graph G star, and Ng of W over G star equal to S, and some such a sequence transform H to a graph H star such that n of W of H equal to S. So, since n of W over H equal to n of W over H, deleting W leaves simple graph. Therefore, G dash equal to G star minus W and H dash equal to H star minus W with degree of V equal to degree of H. V over G equal to degree of V over H for every vertex V. By the induction hypothesis, some sequence of 2 switches transform G dash to H dash. Since these do not involve W and W as the neighbors of G star and H star, so applying the sequence transform G star to H star, so we can transform G to H by transforming G to G star, then G star to H star and reverse the order, and then we get the transform of H to H star. Next, directed graph and its edges. Directed graph means, so you have a vertex, so we have a what arrow, mean each arrow is what towards what direction it goes. So directed graph or digraph, G is a triple, it has a vertex set and edge set, and function assigning edge ordered pairs of vertices, The first vertex V1 is ordered pair is a tail of the edge. So here you say this is a first, then this is a head, this is a tail, like that. The second is a head, and together they are end points. So edge is said to be from its tail to its head. The terms head and tail come from the arrows used to draw the digraph. So here is a digraph. So V1, V2, V3, V4, V5, right. Here V3 is a tail and V2 is a head, like that. Here V1 is a tail and V2 is a head. So as with graphs, we assign each vertex a point in the plane and each edge a curve joining its endpoint. When drawing digraph, we give the curve a direction from the tail to the head. Next, directed graph and its edges. So when a digraph model or a relation and each ordered pair is a head and tail pair for at most one edge. This setting, as with a simple exam graph, we ignore the technicality of a function assigning the endpoints to the edges and simply treat an edge as an ordered pair of the vertices. So in a graph, a loop is an edge whose endpoints are equal. Next, multiple edges or edges having the same ordered pairs of endpoints. A digraph is simple if each ordered pair is head and tail of the most one edge. One loop may be present at each vertex. So this is the example of this. So multiple edges. Here suppose if you V1 to V2 one direct, and V2 and V1 also in another way to V2. Loop also we can denote through the arrow, then it is a directed graph. Loop and multiple edges in a directed graph. So in a simple digraph, we write UV. We write UV for an edge with the tail U and V is a head. There is an edge from U to V. V is a successor and of U, and U is a predecessor and V is a successor. So U graph V for there is an edge from U to V. Next, path and cycle in digraph. A digraph is a path if it is a simple digraph whose vertices can be linearly ordered, so that there is an edge with a tail U and a head V if and only if V is immediately follows U in the vertex ordering. So this is a graph with U and V. The cycle is defined similarly using an ordered of the vertices on the cycle. Underlying graph. Underlying graph of a digraph is a graph G is obtained treating the edges of D as an unordered pairs. So the vertex set and edge set remain the same and the endpoint of an edge are the same in G as in D, but in G they become an unordered pair. So this is a digraph, this is a underlying graph. So here there is a no arrow, here there is an arrow. That is the meaning of difference between line graph, a digraph and underlying graph. So underlying graph are most ideal and method of graph theorem arises to study the ordinary graphs. Digraphs can be useful to additional tool, especially in the application. When comparing digraph with a graph, we usually use G for the graph G and D for the digraph. When discussing single digraph, we often use G. Next, adjacency matrix and incident matrix of a digraph. Adjacency matrix A of G of a digraph G is an entry in position of I comma j, the number of edges from Vi to Vj. Incident matrix of a loopless digraph, we set Mij equal to 1 if Vi is a tail of Ej and Mij equal to minus 1 if Vi is a head of the Ej. So, this is the underlying digraph. Below is the graph of the example. Note the similarities and difference in their matrices. So, W to W there is a no loop 0, W to X no connection, whereas X to W only connection, therefore 0, and then W to Y is connection, right, this is W to Y, therefore this, and W to Z there is no connection, therefore 0. Similarly, X to W is connection, therefore 1, X to X no loop, therefore 0, X to Y there is a connection, therefore 1, and X to Z there is no connection, 0. Now, Y to W is no connection, therefore 0, because not arrow is mentioned, right, and then Y to X, yes, there is a connection, 1, and then Y to Y no loop, therefore 0, Y to Z connection, therefore 1, and there is a no connection from Z to X, Z to W, and then Z to even Y also, because predecessor successor opposite direction, therefore all are 0. Now, coming to the corresponding using the incident matrix. Previously adjacency matrix here is incident matrix. If W to A opposite direction, therefore minus 1, W to B direct connection, therefore plus 1, W to C no connection, therefore 0, W to D no connection, therefore 0, W to E no connection, 0. So, this way we can go X to A 1, X to A. How many X is connected with A incident, therefore 1 A 1, X to B no, therefore 0, X to C yes plus 1, X to D opposite direction minus 1, X to E no connection, therefore 0. So, like that you have to go Y and Z, and we have a incident matrix corresponding to graph G. So, A of G is called as adjacency, M of G is an incident matrix. So, connected digraph, to define a connected digraph, two options come to mind. We could require only that the underlying graph be connected. However, this does not capture the most useful sense of the connection for the digraphs. Next, a weakly and strongly connected digraph. A graph is weakly connected if its underlying graph is connected. A digraph is strongly connected or strong for each ordered pair U comma V vertices. There is a path from U to V, so that is the meaning of digraph strongly connected. U to V and V to U both. Next, Eulerian graph. A graph is said to be Eulerian. It's a trial containing all the edges, mean sum of all the edges is even. So, Eulerian circuit is closed trial containing all edges. So, digraph is Eulerian if it has a Eulerian circuit. So, this is the statement you have to understand. Let G is a digraph with delta G greater than or equal to 1. So, G contains the cycle. The same conclusion hold when delta negative of G is always greater than or equal to 1. So, let P be a maximal path in G, and u be the last vertex of P, and P cannot be extended. So, every successor of u must already be a vertex of P. Therefore, since delta of G is greater than or equal to 1 and u as a successor of V on P, so the edge uv completes a cycle with a portion of P from V to u. So, a graph is said to be Eulerian if and only if d of predecessor of vector minus d of successor of V for each vertex V, and the underlying graph has at most one non-trivial component. Next, de Brugian cycles. The application is there are 2 power n binary string of length n. If there is a cycle arrangement 2 power n of binary digit such that 2 power n strings of n consecutive digital are all distinct. For example, n equal to 4 and we have a binary digit of the works. So, this is 0 0, like that you have to 4 4 4 you have to binary bits you have to do that. Next, we can use such an arrangement to keep track of the position of the rotating drum. One drum has a 2 per n rotational position. The band around the circumference is split into 2 per n portion that can be coded 0 or 1. Sensor read n consecutive portion, and the coding has the property specified above. Then the position of the drum is determined by string read by the sensors. So, to obtain such a circular arrangement, define a digraph dn whose vertices are binary n minus 1 tuple, put an edge from A to B, the last n by 2 entries of a degree of A agree with the first n minus 2 entries of B, label the edge with the last entry of B, and below we show D4. We next prove that Dn is Eulerian and show the Eulerian circuit yields the desired circular Pigeon cycles. So, this is the graph of A to B, right, A to B, and we have a if the last n minus 2 entries A agree with the first n minus 2 entries of B, label the edge with the last entry of B. So, if there is a connection 1 and binary bits you started with 300 and then 001 for this vertex, 100, 110, 010, 1001 and 011 and then 11 like that. So, like how many 3 bits like that you have to do, and 2 power 0, 2 power 1, 2 power 2, 2 power 3 and so on like that. There is a connection and do that, then we have do the a cycle of these ideas. So, the digraph Dn as an application of 25 is Eulerian, and edge labels of the edges any Eulerian circuit is Dn form a cycle arrangement in which 2 power n consecutive segments of the length n are distinct. So, we show that first Dn is Eulerian and the labels on the edges in any Eulerian circuit of Dn form a cycle arrangement in which 2 power n consecutive segment of length n are distinct. So, digraph Dn is Eulerian. So, every vertex has a out degree 2 because we can append a 0 1 to its name to obtain the name of the successor vertex. Similarly, every vertex has in degree 2 because the same argument applies when moving in a reverse and putting a 0 or a 1 in front of the name. So, this is the way we can use the network, start from the digraph. So, digraph Dn is Eulerian. Another way we have to prove Dn is strongly connected because we can reach the vertex B1 to Bn minus 1 form any vertex by successively follows the edges, the label B1, B2 and so on Bn is B suffix n minus 1. Dn satisfies the hypothesis and is Eulerian. So, the labels on the edges in the Eulerian circuit Dn form a cycle and then it has a 2 power n consecutive segments of length n are distinct. So, this is the arrival at the vertex and receiving the vertex and connect the name of the vertex.